the next example is trucks have more tires. So why is it so? So trucks carrying heavy loads have more than 4 tires. More tires in case of trucks increase the area of contact with the road. This results in reduced pressure on the tires. So for this picture, the first picture, the statement trucks have more tires is related to the concept of pressures as it pertains to the distribution of weight in the interaction between the vehicle's tires and the road surface. So when trucks carry heavy loads, the additional tires serve to increase the total area of contact with the road. These increased contact area results in a more evenly distributed pressure across the tires, reducing the pressure on each individual tire. So by spreading the weight of the truck and its cargo over a larger number of tires, the pressure exerted on each tire is reduced. This is beneficial because it helps to mitigate the risk of excessive wear and heat buildup on any one tire. Additionally, reduced tire pressure can contribute to improved traction and stability, especially when the truck is navigating challenging and terrains or adverse weather conditions. So, in essence, the presence of more tires on trucks carrying heavy loads is a design of feature intended to address the impact of pressure, ensuring that the vehicle can effectively manage the weight it bears while promoting safety and minimizing the risk of tire-related issues. So, this is the trucks have more tires. So, for the next example is the ink dropper. So this is also another pressure example. So ink dropper works on the principle of air pressure. On squeezing the rubber top on the dropper, the air is squeezed out. Now when you put the tip of the dropper into the liquid and stop squeezing the top, the low pressure inside the ink flows inside the fill of the void. So the statement ink dropper, based on this second picture, the ink dropper, it works on the principle of air pressure and connected to the concept of pressure, specifically in the context of how ink droppers function. The operation of an ink dropper involves the manipulation of air pressure to facilitate the movement of ink. When you squeeze the rubber top of an ink dropper, you compress the air inside the dropper, forcing it out. This action creates a region of low pressure inside the dropper. When the tip of the dropper is placed into a liquid and the pressure on the rubber top is released, the low pressure environment inside the dropper allows the surrounding higher pressure liquid to flow into the dropper, filling the void left by the displaced air. So this principle illustrates how changes in air pressure can be harnessed to control the movement of liquids, in this case, allowing ink to be drawn into the dropper. By manipulating air pressure, the ink dropper provides a practical example of how pressure differentials can be utilized to facilitate fluid transfer, so demonstrating the fundamental role of pressure in everyday process and technologies. So these are the examples of things that has pressure in it. So let us calculate the pressure exerted in the bottom by the weight of the fluid. So that pressure is the weight of the fluid or mg divided by the area or A supporting it. The area of the bottom of the container is, as you can see, it is P equals mg over A. So we can find the mass of the fluid from its volume and density. So M equals PV. The volume of the fluid V is related to the dimension of the container. It is V equals AH. So where A is the cross-sectional area and H is the depth. Combining the last two equations gives M equals PAH. If we enter these into the expression for pressure, we obtain P equals open parenthesis PAH close parenthesis G times G over AA. A. The area cancels and rearranging the variables results to P equals HPG. So pressure due to the weight of a fluid. So this equation, open parenthesis, P equals HPG, close parenthesis, represents the pressure due to the weight of any fluid of average density P at any depth or H below its surface. So for liquids, which are nearly incompressible, this equation holds to great depths. For gases, which are quite compressible, one can apply this equation if the density changes are small over the depth considered. So these are the way or the formula on how to calculate the pressure exerted on the bottom of by the weight of the fluid.
So now we will proceed to sample problem number 1. So if a force of 10 Newton acts over an area of 5 meters squared, what is the pressure? So now we will solve the problem. So the given are force is equals to 10 Newton and the area is equals to 5 meters squared. So the solution is pressure is equals to force over area. So 10 newtons over 5 meters squared is equals to 2 newton over m squared or 2 pascals. Sample problem 2. A box weighs 100 newtons and exerts a pressure of 50 newtons per meter squared. What is its area? So the given are force is equals to 100 newton and pressure is equals to 50 newton per meter squared. So the solution for finding the area is this. 50 newtons per meter squared is equals to 100 newtons over area. So in order to transfer area to another side is you need to cross multiply. So 50 newton per meter squared times area is equals to 100 newtons. So in order to cancel 50 newton meter per squared, to remain the area is divided to itself. So 50 newton over meter squared per meter squared over divided by 50 newton per meter squared, and also the same with the other side. So 100 newton is over 50 newton per meter squared. So the answer would be the area is 2 meters squared. So the easier explanation for variation of pressure with depth in a fluid is imagine yourself swimming in a pool. So the deeper you go, the higher the pressure because the water above you will create pressure because of gravity, and that explains how pressure increases as you go deeper.
Discussion on sample problem 1. Although this force seems large, it is small compared with the 1.96 times 10 raised to the power of 13 newtons weight of the water in the reservoir. In fact, it is only 0.0800% of the weight. Note that the pressure found in part A is completely independent of the width and length of the lake. It depends only on its average depth at the dam. Thus, the force depends only on the water's average depth and the dimensions of the dam, not on the horizontal extent of the reservoir. In the diagram figure 2, the thickness of the dam increases with depth to balance the increasing force due to the increasing pressure. So, in sample problem number 1, the discussion highlights that despite the apparent magnitude of the force involved, it is relatively small when compared to the weight of the water in the reservoir. So specifically constituting only 0.0800% of the total weight. Notably, the pressure calculated in part A is entirely independent of the lake's width and length, so emphasizing its dependence solely on the average depth of the dam. The force exerted is determined by the water's average depth and the dam's dimensions. So with no influence from the horizontal extent of the reservoir, the accompanying diagram in figure 2 illustrates that the dam's thickness increases with depth, a design strategy to counterbalance the escalating force resulting from the rising pressure. So in sample problem number 1, the discussion highlights that despite the apparent magnitude of the force involved, It is relatively small when compared to the weight of the water in the reservoir. So specifically constituting only 0.0800% of the total weight. Notably, the pressure calculated in Port A is entirely independent of the lake's width and length, so emphasizing its dependence solely on the average depth at the dam. The force exerted is determined by the water's average depth and the dam's dimensions. So, the dam's dimensions, which is height, width, and length. And with no influence from the horizontal extent of the reservoir, the accompanying diagram in figure 2, this illustrates that the dam's thickness, its thickness, increases in depth and design strategy to counterbalance the escalating force resulting from the rising pressure. Atmospheric pressure is another example of pressure due to the weight of a fluid. In this case, due to the weight of our air above a given height, the atmospheric pressure at the Earth's surface varies a little due to the large-scale flow of the atmospheric induced by the Earth's rotation. So this creates weather highs and lows. Atmospheric pressure serves as an illustrative example of pressure arising from the weight of a fluid, so it's specifically attributed to the mass of air above a particular elevation. The atmospheric pressure experienced at the Earth's surface undergoes slight fluctuations due to the expansive atmospheric circulation, so induced by the planet's rotation. So, resulting in the formation of weather highs and lows. This dynamic interplay within the atmosphere contributes to the variations observed in atmospheric pressure, reflecting to the intricate relationship between Earth's rotation, atmospheric flow, and the resultant pressure patterns.
So, sample problem number 3. Calculate the average pressure and force exerted. What force must a dam withstand? So, the given is the dam is 500 meter wide and the water is 80 meter deep at the dam. And what we need to find is the average pressure on the dam due to the water, and we need to calculate the force exerted against the dam and compare it with the weight of water in the dam, which is 1.96 times 10 to the power of 13 newtons. So here is the strategy for A, which is how to find the average pressure. So the average pressure due to the weight of the water is the pressure of the average depth, which is H is equal to 80 meter. And we need to divide it by 2 since the pressure increases linearly with depth, and the answer of that is 40 meter. So entering the density of water, which is 10 cube kilogram over m cube, and taking H to be the average depth of 40 meter, and the gravitational force, which is 9.8 meter per second squared or 9.8 newton over kilogram. So we obtain average pressure equals 40 meter for the depth and 10 cube kilogram over meter cube for the density times 9.8 newton over kilogram for the gravity. And the answer of that will be 3.92 times 10 to the power of 5 newton over meter squared, or 3.92 times 10 to the power of 5 Pascal. So we have already found the value for the pressure, and now we're going to find the force. So to find the pressure, we're going to the force, we're going to times the pressure and the area. And the area of the dam is area equals length times width. So to find the area, we're going to times the length and the width of the dam. And the length of the dam is 80 meter times the width, which is 500 meter, equals 4.00 times 10 squared meter squared. So force equals pressure times the area. And the pressure equals 3.92 times 10 to the power of 5 newton over meter squared from the previous solution, times the area, which is 4 times 10 squared meter squared. And the answer for that is 1.57 times 10 to the power of 10 newtons. So for sample problem 4, we are going to calculate the average density of how dense is the air. So calculate the average density of the atmosphere given that it extends to an altitude of 120 kilometers. And we're going to compare this density with that of the air, which is 1.29 times 10 to the power of negative 3 kilometer per meter cube. So the strategy for this is, if we solve P equals HPG for density, we see that P equals pressure over depth times the gravity. So we then take P, which is the atmospheric pressure, to be 1 atm, and the H, which is the depth, is given, and G is also known. So we can use this to calculate the density. So for the solution, we enter the known values into the expression for density, results to density equals. So if we divide the numerator, which is 1.01 times 10 to the power of 5 Newton over meter squared, that is the pressure, over the denominator, which is 1.176 times 10 to the power of 6 Nm over kilogram, which is from the depth times the gravity. The answer would be density equals 8.59 times 10 to the power of negative 2. And since they have the same numerator, we're going to cancel this. So we're going to cancel Newton from the numerator and the Newton of the denominator of the other values. So the answer of that will be density equals 8.59 times 10 to the power of negative 2 kilogram over meter cube. So that is the final answer for the density.